So, welcome back again. So, in this class, we are going to discuss the interference due to reflected light in thin films. We have discussed what is interference due to division of amplitude. So, we have discussed in the last class what is a thin film, and here we are discussing the interference due to reflected light in a plane parallel thin film. So, what is a plane parallel thin film? It is a transparent thin film of uniform thickness surrounded by two parallel surfaces. And such a film is known as a plane parallel thin film. And when light is incidenting on such films, a small portion of this light gets reflected from the top surface and majority of the portion is transmitted into the film. And we are discussing, and again this process is repeated, and the thin films generally transmit incident light strongly and reflect only weakly. After 2 or 3 reflections, the intensities of reflected rays drop to a negligible strength. And we generally consider the first 2 or 3 reflections. And these 2 rays are derived from the same incident ray. Firstly, a ray is hitting on the interface of the film, and later on this gets divided into reflected ray and transmitted ray. So initially there is only a single ray, and since all these reflected rays are derived from a single incident ray, we generally call them to be coherent sources. And we know already that the prerequisite for the occurrence of interference is that the sources should be coherent. The sources and considered to be coherent, and the reflected waves which are reflected from the top surface of the film normally traverse parallel path and interfere at infinity, and it is basically called the 2B interference. Okay, and the condition for the constructive and destructive interference we have already mentioned before. Now we'll discuss what's happening basically when the light gets reflected and transmitted in thin films. So we consider a thin transparent film of thickness, uniform thickness T. Thin transparent film of uniform thickness T thin transparent film of uniform thickness T, and T is the thickness of the film. T is the thickness of the film, and this film is bounded by 2 plane parallel surfaces, and the refractive index of the material of the film is mu, and I am mentioning it to be refractive index is represented as mu, and the film is surrounded by air having refractive index 1. Let us consider plane waves from a monochromatic source which is falling on the film at an angle of incidence I. So first, for having the angle of incidence, I need a normal first. So I'll draw a normal. I'll draw a normal here. Suppose I'm having a normal here, and I'm having a incident ray. I'm having an incident ray. Okay. It is at an angle of incidence, and I am having a reflected ray satisfying the conditions for incidence and reflection, and I can mention, okay, I can mention the angle of incidence to be I, and angle of reflection to be R. This is the incident ray, this is the reflected ray, this is the normal. And what happens next is I'll have a part of the ray and I'm going to name this rays. I'm going to name it as A, and this is, I'm going to name this as B. I'm going to name this as B. This is B, and this is named as C. And we are having again, okay, this is the transmitted ray. Normally 96% is transmitted and 4% is reflected back, and reflected ray is BC and the transmitted ray is named as BF. Transmitted ray is named as BF into the film. The transmitted ray makes an angle R with the normal at the lower boundary surface, and I am going to draw again a normal here. It makes, sorry, I'm going to draw a normal here. So I'll have a again a ray. It will be reflected, and this is the transmitted ray. This ray is the transmitted ray, and here also I'll have another ray which is transmitted. Okay, so I can name this to be making an angle R. This is the, suppose this is R, this is R, and I'll name this as I. Angle of incidence is equal to angle of reflection, means this both I'm going to name it as I, and the other both I'm going to name it as R. Now I can name this is actually F. This is F. BF is the transmitted ray, and at the lower boundary surface the rays again get reflected and transmitted, and here the reflected ray is FD, and those which is coming out as the transmitted ray again is DE, and here the ray is named as FK, which is traversed out from the thin film. Okay, the ray BF is partly reflected back into the film along FD, while a major part is refracted as FK out from the film. Part of the reflected ray FD is transmitted to the upper surface and travels along DE. Since the film boundaries are very much parallel, the reflected rays BC and DE, this is BC and DE, they may be parallel since the thin film is having a parallel surface. The rays traveling along BC and BFDE are derived. The rays traveling along BC and BFDE are derived from a common incident ray which is called as AB. So I can say these are the coherent sources, and these are coherent, and when they interfere it can produce interference pattern when we view with our eyes. Okay. So here I am having the medium. It is having a refractive index mu. This medium is having a refractive index mu. Right. I'm going to drop this. Okay. This is the medium having refractive index mu. Okay. Okay, so now we'll discuss what is the path difference. And here I can see DH. Suppose I'm drawing a perpendicular from D to meet the line BC at a point H. Okay, now I can say this path length HC is approximately equal to D. HC is equal to D. So what makes the path difference between these two interfering beams is this quantity BF. The first ray is having a path length BC and second ray is having the path length BF, FD, DE. And here the HC is equal to DE. So what makes the difference is BF plus FD for the second ray and BH for the first ray. So I can write it as the geometrical path difference. I can write it as geometrical path difference. Geometrical path difference is equal to what? BF plus FD minus BH. BH plus FD minus BH. BF plus FD minus BH. And now I have to make it to be the optical path difference. So for that I will have to multiply with the refractive index of the medium through which it travels. Okay. So I can find it here that BF and FD are the ray paths in a medium of refractive index mu and BH is traveling in air. So I can notate the path difference, the optical path difference as delta. Optical path difference delta is equal to, this is the optical path difference, and I can write the optical path difference to be mu into, I can write it mu into I can draw mu into BF plus BF plus FD minus, and it is 1 into BH, minus 1 into BH. Okay, so next our intention is to find out what is BF, what is FD, what is BH. For that we consider triangle BFD. Consider this triangle BFD, and I can say BFG and BFG. Okay, suppose I'll have to draw one thing here. I have to make it meet. Okay, it should meet here. Meet here at the point G. Right. Okay. I have to make it triangle. Now I can say in triangle BFD, what happens? In triangle BFD, these two angles are equal. These two angles that we know. Incident ray is equal to angle of incidence is equal to angle of reflection. And this the side FG is common. Side FG is common, and BF is equal to FD. They are traveling the same path within the plane parallel thin film. Okay, so they are similar triangles. So what happens next is I have to find out what is BF. BF is what? For getting BF, I'll have to put cos R. Cos R is adjacent. Adjacent side is FG by hypotenuse, and hypotenuse is BF. So I can write cos R. Cos R is equal to, actually it is small r. Cos R is equal to, what I can write is, cos R is FG by, cos R is FG by BF, or I can write BF is equal to, or I can write BF is equal to FG by cos R, FG divided by cos R, and that can be written equal to, that will be equal to what? FG is what? FG is the film actually, and the film is having a thickness. Film is having a thickness T, that I have already mentioned in the beginning. The thickness of the film is small t. So I can write it here as small t divided by cos R, small t, and BF is equal to small t divided by cos R, small t divided by cos R. So what happens if it is BF plus FD? And if it is BF plus FD, it will be BF is equal to FD. We all know from similar triangles, both those two triangles are similar, means I'll be getting a result BF is equal to FD, BF is equal to FD, and I've got BF to be T by cos R, then BF plus FD will be what? BF plus FD is equal to 2T divided by cos R. Okay. So you got BF plus FD is equal to 2T by cos R. And I am having BG is equal to GD. And it is again a similar triangle, that is this side. And we have got BF is equal to FD. And in this equation, I need what? I need BF plus FD. And I have got BF plus FD is equal to 2T by cos R. So next I will have to find out what is BH. For that we start with BG and DG, and BG is equal to DG. I'll write here. I can write it here. Okay, I can write it here. Okay, it is BG. BG is equal to what? BG is equal to DG. BG is equal to DG, right? And BD will be equal to what? BD. From that I can write. BD will be equal to what? Means this side. BD will be equal to 2BG. Will be equal to 2BG. BD will be equal to 2BG. And from this triangle, I have to find out what is tan R. What is tan R in terms of BG and FG. So I'll write tan R is equal to, I can write tan R is equal to BG by FG. Tan R is equal to BG by FG. And I can write BG is equal to FG into tan R. From that I can write BG. From that I can write BG is equal to what? BG is equal to FG into tan R. FG into tan r, Bg is equal to Fg into tan r. And what is Fg? And I got Fg is again small t. So what I'll be getting is t into tan r. That is equal to t into tan r. So what I've got is Bg is equal to t into tan r. But what I'm having is BD. BD is equal to 2BG. So I can write BD is equal to 2BG and BG is equal to T tan r. So I can write BD is equal to 2R tan R. BD is equal to 2R tan R. Okay, 2R tan R. So this is an important result. BD is equal to 2R tan R, and I am having BF plus FT is equal to 2R by 2T by cos R. Now again, if I am taking angle HBD, if you are taking angle HBD, this angle is I degrees and this is normal, means this angle will be 90 degree minus I. So I'll get angle B, I'll get angle HBD. Angle HBD, right? I can write it like this way. Angle HBD, angle H, you can take it a bit, angle HBD, angle HBD is equal to what? Is equal to 90 minus I. Angle HBD is 90 minus I. Okay. HBD is 90 minus I. And what is BH? What is sin I? If I am considering again here, what I'll be getting? If I am considering the triangle BHD, and if you considering this triangle BHD, and this angle is I means normally this angle will be 90 minus I. This is 90 degree. This angle is 90 minus I. This is 90 degree, means this will be what? It will be normally I degrees. So I can name that total, it should be 180 degree. This is I. This is the perpendicular. This is I actually. This is the perpendicular dot 90 degree. This is 90 minus I. So not to get total 180 degree, this angle should be I. Right. It is, that logic you are taking here. You can use it to be right for you to understand. Okay, this angle is I. Okay. So you have got it. From this I can write down sin I is equal to, I can write sin I is equal to sin I is equal to BH by BD. That is sin I is equal to opposite by hypotenuse. That is BH by BD. That is BH divided by BD. BH divided by BD. And from that I'll get what is BH. We'll get BH as BH is equal to sin I into BD. You'll get sin I into BD. Sin I into BD. BH is equal to sin I into BD. Okay. BH is equal to sin I into BD, and you know what is BD. BD is what? 2BG. BD is 2R tan R. Sin I into 2R tan R. Right. Sin I into 2R tan R. So I can write it as is equal to sin I into uh, sin I into 2r tan r. Sin I into 2r tan. From that I can obtain BH. You already have written what is BH, right? It is 2r tan r into sin I. And from Snell's law, you can write, from Snell's law, what you can write is sin I by sin r is equal to refractive index of the medium, that is mu. Sin I by sin. I'll do it again. Okay. Sin I by sin r is equal to sin I by sin r is equal to mu, which is the refractive index of the medium. Okay. Sin I by sin r is equal to mu, which is the refractive index of the medium. From that I can write sin I is equal to mu into sin r. I'll write it like this way. Sin I is equal to sin I is equal to mu into sin r. Mu into sin r. Sin I is equal to mu into sin r. So from that I can write BH. From that I can write instead of sin I can write mu into sin r. So for that I will get BH is equal to instead of sin I I'll write mu sin r, then 2t tan r. That is I can write 2r tan r. So 2r tan r into mu. Instead of mu I'll write u sin r. Okay. Instead of mu I'm writing u. Okay. 2r sin r into mu sin r. And what is tan r? It is sin r by cos r. So I can write it again to be BH to be BH is equal to 2r t 2r t sin square r. Okay, sin square r, or I'll write as sin r into sin r divided by cos r. Sin r into sin r divided by cos r. 2 mu t. 2r t. I mean 2 mu t sin r. Okay. That minus 2r. Okay, t into tan r. Okay, 2 into t tan r. So this mistake I made here. So it is not r actually, it is 2t. Okay, 2t tan r. Okay, what I have written here is 2r tan r. Oh, it's not 2r tan r, it is 2t tan r. Okay, just change it. This 2t tan r. That is 2t tan r. What I have written is r. Okay, you just make a change. It is not r. I just misspelled it. It is actually t. So you have to change it here and all. Instead of r, you'll have to write it as t here. Then it will be clear. Here also instead of r, you'll have to write it as okay. Instead of r, you can write it as t. Instead of r, you can write it as t. So what I'll be getting is BH is equal to BH. You'll be getting BH is equal BH is equal to BH is equal to 2t 2t u sin square r by cos r. Sin r by cos r. 2t u sin r by cos r. U is mu. Okay. So So this is what we have got. Okay, so we'll have to start with this one. Here I have the expression for my path difference, optical path difference to be mu into Bf plus Fd, that is Bf plus Fd minus Bh. Bf plus Fd minus Bh. Bf plus Bf plus Fd. Fd minus BH. BF plus FD minus BH. 2 mu T sin R into sin R divided by cos R. So we'll get the path difference to be what? Mu into BH. What I'll be having is BF plus FD. And I've got BF plus FD is equal to 2T by cos R. So I can write what I've got the delta to be. Okay, I'll write delta here. Delta is equal to the path difference. Delta is equal to I can write it to be U into refractive index U. Instead of mu I'm writing as U. U into it is 2T. 2T by cos R. It's written here 2T by minus 2T by cos R minus you will have 2 mu T sin R into sin R by cos R. 2 mu T sin R into sin R by cos R. Okay. This is the path difference you are going to get, and I can take 2 mu T cos R, which is common in both the cases, and what will be left is 1 minus sin square R. 1 minus sin square R is cos square R, and cos R into cos square R get cancelled, and what will be left is delta is equal to, and what will be left is equal to our optical path difference will be 2 ut 2 ut cos R. Okay, this is what you will be getting as your optical path difference, and I am going to notate the optical path difference as delta. Okay, delta. I'll notate the optical path difference as delta. You can notate the optical path difference as delta, which is 2 mu T cos R. And this happens. Okay, this is delta. And the next condition is if you are here, what's happening is that the light gets reflected from a rarer medium. It hits here and hits the denser medium. Okay, it is traveling, hitting the denser medium. It is reflected back. Normally, there will be a path difference of lambda by 2 or phase difference of pi. I have already mentioned in the beginning of the class, that is indifference by division of amplitude. So I'll have to put, and here, in this case, one more path difference in addition to BH, one more path difference occurs due to reflection, and that path difference is lambda by 2 if lambda is the wavelength of the light used. So the path difference, one more thing will be added here, 2 mu T cos R minus lambda by 2. Okay. So this condition is a very important condition. You just study this. Lambda is equal to 2 mu T cos R minus lambda by 2. Delta is equal to. It is the path difference which is introduced. Path difference which is introduced due to the light rays interfering, or the light rays which are reflected from the reflected light rays from the plane parallel thin film, and they are undergoing indifference conditions. The path difference introduced is 2 mu T cos R minus lambda by 2. Okay. So I think with this we stop our class here. We have in this class we have discussed only the derivation, that is the derivation which gives you the optical path difference for the light waves which are actually interfering, or the reflected light which gets interfered to obtain the interference pattern from a plane parallel thin film. Hope it is clear for you. Just keep in mind this is very important, and many questions or many problems are asked from this part, and we'll discuss the condition for constructive indifference, destructive indifference, and some examples. And some more portions are yet to be discussed in the following class. So I think we are running out of time really. So we'll stop here. We'll continue it in the next class. You just write down the notes, and if you are having any doubts, you can come to me personally. Okay, thank you.